Today, in this video lecture, we will see chapter 4 of Strength of Material subject, and chapter 4 is Strain, Energy and Impact. First, we will see introduction of this chapter in this lecture, and we will see strain energy in a member subjected to axial force. Then we will see resilience, proof resilience, modulus of resilience and modulus of toughness in this video lecture. So first, start with our introduction. When a load is applied on an elastic body, it gets deformed. That means the work is done by the load on a body. See, this is consider this as a rectangular body. And applied tensile force P. Due to this applied load P, there is deformation occur in this body. See, this dotted deformation, change in length occurs in a body due to this applied tensile force P, and it gets deformed. This is deformation. That means the work is done by the load on a body. See this first bullet point. When a load is applied on an elastic body, it gets deformed. That means the work is done by the load on a body. Due to this applied tensile force P, this body gets deformed. And that means the work is done by the load on a body. Second bullet point is, this work done is stored in a body is called as strain energy or resilience. Due to this applied tensile force P, there is elongation occurs in this body. And there is work done is stored inside this body. For this second bullet point explanation, we will consider as a this rigid body, and when we applied force, random force as P on this body gets deformed. It's change its length. See, this dotted portion is deformation of this body, and this P load acting on this body, that means work is done on this body, and this work done is stored in a body is called as strain energy. Due to this P force acting on this body change its shape, and here see this body store its energy. When we remove this load, the body regains its original position because of this store energy. So it can be easily visualized in springs. When the spring is loaded, it gets compressed and regain its original position immediately when the load is removed. In case of springs, we will also see this. Consider this as a spring, and when we apply load to this spring gets deformed like this, like somewhere here. And when we remove this load, this spring gets its original position. And why this spring gets its original position? Because of this strain energy. And this amount of strain energy stored in a body, it depends on the type of loading. That means axial load, bending load, shear load, torsional load, etc. Next, we will see strain energy in a member subjected to axial force. So, first consider a member subjected to load P having cross-sectional area A and length L. let delta L is equal to elongation in the bar and sigma is equal to maximum stress induced in the member. This bar subjected to tensile load P and length of this bar is capital L. And load versus deformation diagram is on y-axis load and on y-axis deformation, x-axis deformation. So as load increases, deformation increases. So there is gradually applied load. So when a load P acted on a body, it undergoes deformation delta L. Due to this P load acting on body, tensile load P, this member gets deformed like this. It changes shape. Somewhere delta L. And the graph plotted load versus deformation like this. And we know strain energy stored in a material is equal to area under the load versus deformation curve. See, strain energy stored in this material is area under load versus deformation curve. This is curve of load versus deformation and area under this. That means see strain energy stored is equal to work done by the load. That means and strain energy denoted as U and work done under the load. That means the strain energy stored in a material is equal to area under the load versus deformation curve. And area of this triangle is half. This is P load. Load is here denoted as P. And multiply by deformation denoted as delta L. And this is triangle, and triangle area is half this side and this side. Half height into width. So strain energy store U is equal to half load into deformation. And we all know that see stress is equal to load upon area. That means this load is equal to stress multiplied by area. So here this load is nothing but stress multiplied by area. And this delta L, we all know that E, Young's modulus, is equal to stress upon strain. and stress is load upon area, and strain is change in length upon original length. So this change in length is, see this E, this P by A as it is, P by A, that means this stress. Put this stress as it is upon delta L upon L. Here E multiplied by delta L upon L is equal to stress. That means this delta L, here delta L, this delta L is nothing but stress multiplied by length divided by E. Mathematically we solve it. See, this is delta L, and put this delta L in this strain energy equation. This delta L is stress multiplied by length of that member upon modulus of elasticity. Therefore strain energy store is equal to the sigma 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 square upon this 2 into E and AL, area into length. See, for that bar, area multiplied by length is volume of that bar. So sigma square upon 2E multiplied by volume. Area into length is nothing but volume. Right here. Volume. So this is formula of strain energy store. U is equal to sigma square upon 2E into volume. Strain energy denoted as U is equal to sigma square stress square upon 2 into modulus of elasticity into volume. Now next we will see concept of resilience, proof resilience, and modulus of resilience, and this modulus of toughness. Resilience is nothing but the energy which is stored in a body within elastic limit is called as resilience. See, this word is important. Within word is important, and elastic limit word is important in this resilience definition. For that explanation, we will see stress versus strain graph for mild steel. I had explained this stress versus strain graph in our chapter 1, stress and strains. We will see this again. See, consider this as a y-axis, this as a x-axis, and on y-axis this as stress, and on x-axis this as strain. And stress versus strain graph for mild steel is like this, up to this proportional limit, up to this elastic limit, and like this. This is, consider this as a point A, this as a point A, and this point A is nothing but proportional limit. And this next, this as point B, and this is elastic limit. And see definition once again, the energy which is stored in a body within elastic limit. Within that means within elastic limit. That means below that elastic limit, and below elastic limit is point A, this point. And this energy, the energy which is stored in a body within elastic limit, is called as resilience. And we all see this strain energy U is equal to sigma square upon 2E into volume. That means see, this half as it is, this sigma, consider as it is, this sigma upon E. Just mathematically resolve this formula. Half this sigma is nothing but stress, and this sigma upon E is sigma is equal to E is equal to stress upon strain, and small e is equal to stress upon E. That means this is strain. This equation is strain, and multiply by volume. That means this strain energy is half stress into strain into volume. Next concept is proof resilience. The maximum strain energy which can be stored in a body up to elastic limit is called as proof resilience. So see difference between resilience and proof resilience. Here within word is not accepted in this proof resilience definition. Here up to word is important, up to elastic limit. That means up to this B point. That means up to here. And formula for strain energy is same, only difference is this stress is strain energy stress up to strain energy stress. See, stress in this up to elastic limit is different. Here stress, and up to within elastic limit, that means up to this point a stress is here. So this is difference, sigma square upon 2. E is same, modulus of elasticity, and volume is also same. Next definition is modulus of resilience. Modulus of resilience is nothing but the maximum strain energy stored in a body up to elastic limit per unit volume. See here, per unit volume term comes maximum strain energy stored in a body up to elastic limit. That means this is proof resilience. Proof resilience per unit volume is modulus of resilience. That means this modulus of resilience is nothing but the this proof resilience divided by, that means per unit volume. And see, proof resilience formula is sigma E square upon 2E multiplied by volume and divided by volume. Volume gets cancelled. So modulus of resilience is sigma E square upon 2E. So this is introduction of this chapter, strain energy and impact. First we had seen introduction. In this introduction we seen strain energy. When a load is applied on a body, it gets deformed. That means the work is done on the body by the load of this body. Work is done by the load on this body, and the work is stored in a body is called a strain energy and deformation. See, due to this P load, there is work applied on this body, and due to this work and due to this P load, there is deformation occurs in this body. This is deformation. Deformation, that means change in length upon original length. And here energy is stored due to this applied load, and this work done is stored in a body is called as strain energy or resilience. Next we will see strain energy in a member subjected to axial force. This is axial force, or you may call this tensile force P. And due to this tensile force, strain energy in a member formula is U is equal to sigma square upon 2E into volume. And here resilience is nothing but energy which is stored in a body within elastic limit is called as resilience. Proof resilience is maximum strain energy which can be stored in a body up to elastic limit. Resilience, that means energy stored in a body within elastic limit. Proof resilience, that means maximum strain energy which can be stored in a body up to elastic limit. And modulus of resilience is proof resilience divided by volume. Formula for resilience and proof resilience is same. U is equal to 1 by 2 sigma square upon 2e into volume. Only this sigma here proof resilience, this sigma is sigma e square, and modulus of resilience is formula is different, sigma e square upon 2e. Here volume is not. And modulus of toughness is work done on a material in a simple tension up to fracture. Work done on a material in a simple tension up to fracture. See, this up to fracture word is important here. This is modulus of toughness. So this is our introduction for strain, energy and impact chapter. Thank you very much.